Stress and strain are fundamental concepts that are used to describe how a body responds to external loads. In this video, we'll explore these concepts using the simple example of a loaded bar. Here we have a solid metal bar that is loaded by two equal but opposite forces. We refer to this as uniaxial loading, because all of the applied loads are acting along the same axis. The two forces are pulling the bar, causing it to stretch. Internal forces will develop within the bar to resist these applied forces. We can expose these internal forces by making an imaginary cut through the bar. I chose to remove the right side of the bar, but I could have removed the left side instead. For any imaginary cut like this one, the internal forces develop in such a way that equilibrium will be maintained. In this case, the effect of the internal forces acting on the cross-section created by our cut will be equal to the effect of the applied external force. I have represented the internal forces as four separate forces here, but I could have represented them as 1 or even 20 forces. In reality, the internal forces are distributed over the entire surface of the cross-section. For this reason, it doesn't make much sense to talk about specific internal forces. Instead, it is better to talk about stress. Stress is a quantity that describes the distribution of internal forces within a body. It makes it easier to discuss the internal state that develops within a body as it responds to externally applied loads. Stress is a measure of the internal force per unit area, and so has units of newtons per meter squared in SI units, and pounds per square inch in US units. Newtons per meter squared are also called pascals. In the case of our axially loaded bar, the internal forces are acting perpendicular to the direction of the cut we made. This type of stress is called normal stress. We can calculate the normal stress in our bar as the applied force F divided by the cross-sectional area A of the bar. It is denoted by the Greek letter sigma. One reason being able to calculate stresses is important is because it allows us to predict when an object will fail. Let's say our bar is made from mild steel, which has a strength of 250 megapascals. The bar will fail when the stress within it exceeds the strength of the material. If our bar has a diameter of 20 millimeters, for example, we can calculate that it will fail if the applied force is larger than 79 kilonewtons. Normal stress can be either tensile or compressive. In this case, the stress is tensile, because the forces are stretching the bar. If the forces were trying to shorten the bar, we would have a compressive stress. The sign convention that is normally used is that tensile stresses are positive values and compressive stresses are negative values. In the case of our bar, it is reasonable to assume that the stresses are distributed uniformly across the cross-section and along the length of the bar. But this is a very simple scenario. The stress distribution in a beam that is bending, for example, will be more complex. Stresses will be tensile on one side of the cross-section, but compressive on the other. Strain is a quantity that describes the deformations that occur within a body. If we fix our bar at one end and apply a force to the other end, the force will cause the bar to deform. The normal strain within our bar associated with this deformation can be calculated as the change in length of the bar delta L divided by the original length L. Strain is a non-dimensional quantity and is often expressed as a percentage. Normal strains can be tensile or compressive. I mentioned earlier that the concepts of stress and strain are closely linked. The relationship between the two can be described using a stress-strain diagram. Stress-strain diagrams are different for different materials. We can obtain the diagram for a specific material by performing a tensile test. This involves applying a known force to a test piece and measuring the stress and strain in the test piece as the applied force is increased. Stress-strain diagrams for ductile materials like this one show that there is an initial region for low strain values where the relationship between stress and strain is linear. Deformations occurring in this region are fully reversed when the load is removed, and so are said to be elastic. This linear relationship between stress and strain is defined by Hooke's law. The ratio between stress and strain is called Young's modulus, which is an important material property. Hooke's law usually only applies for small strains. For larger strains, the relationship between stress and strain is no longer linear. Deformations are not reversed when the load is removed, and we have permanent plastic deformation. You can learn more about stress-strain curves in my videos about Young's modulus, and about material strength, ductility, and toughness. So far, we have only talked about normal stress, which is stress acting perpendicular to a surface. The other type of stress is shear stress. If our bar isn't loaded along its axis, but instead perpendicular to its axis, like this, the internal forces that develop within it are oriented parallel to the bar's cross-section. These internal forces are called shear forces. Shear loading is common in bolts, for example. Once again, it is helpful to use the concept of stress to talk about the internal shear forces within the bar. Shear stress is denoted by the Greek letter tau and can be calculated in a similar way to normal stress as the applied force F divided by the cross-sectional area A. This is actually an average shear stress, since the internal forces will not be distributed evenly across the cross-section. We can better understand shear stresses by looking at the stresses acting on a small element within our bar. We have a shear stress on one face of the element, but the element needs to be in equilibrium, so we must also have shear stress on the opposite face, in the opposite direction. And to maintain rotational equilibrium, we must also have two additional shear stresses, as shown here. These four stresses all have a magnitude equal to tau, and define the shear stresses acting at a single location. Shear stresses cause a rectangular object to deform, like this. We have deformation, so of course we also have strain. Shear strain is defined as the change in angle shown here, and is denoted by the Greek letter gamma. Hooke's law also applies for shear stresses and shear strains, but the ratio between them is the shear modulus G instead of Young's modulus. Although I have discussed normal and shear stresses separately so far, the stress state at a single point within a body will actually have components in both the normal and the shear directions. The magnitudes of the normal and shear components will depend on the angle of the plane we are using to observe the stresses. In our bar with uniaxial loading, the plane we used to make the imaginary cut was perpendicular to the axis of the bar, and so we had normal stresses but no shear stresses. If we instead use an inclined plane to cut the bar, we will have both normal and shear stress components. The stress element is commonly used to represent the stresses acting at a single point within a body. This is the stress element showing the normal and shear stresses acting at a single point for a two-dimensional case. For a three-dimensional case, the stress element looks like this. That's it for this introduction to stress and strain. Having a solid understanding of these concepts will be important for grasping more advanced topics like torsion and beam bending that I will cover in separate videos. If you are interested in learning more about normal and shear stresses, I recommend that you watch my video about stress transformation next. As always, Please remember to subscribe if you enjoyed the video.
Die Analyse von Problemen der Festkörpermechanik in 3 Dimensionen kann sehr mühsam sein und sehr schnell sehr kompliziert werden. Glücklicherweise gibt es in vielen Fällen einige Vereinfachungen, mit denen wir ein dreidimensionales Problem auf ein zweidimensionales reduzieren und so die Lösung erheblich erleichtern können. Die beiden wichtigsten Vereinfachungen, die in der Festkörpermechanik häufig verwendet werden, sind die Bedingungen der Ebenenspannung und der Ebenendehnung. In diesem Video befassen wir uns mit der Ebenenspannung. Was bedeutet nun die Ebenenspannung? Ein Bauteil befindet sich im Zustand der Ebenenspannung, wenn alle auf es einwirkenden Spannungen in derselben Ebene liegen. Überraschend viele gängige technische Probleme können an ebene Spannungszustände angenähert werden. Dies ist am relevantesten für die Analyse dünner Bauteile. Schauen wir uns ein Beispiel an. Um festzustellen, ob wir diese Lochplatte mit Annahmen über ebene Spannungen modellieren können, müssen wir prüfen, ob die Annahme sinnvoll ist, dass alle Spannungen in derselben Ebene wirken. Alle Lasten werden in derselben Ebene, der XY-Ebene, aufgebracht. Das ist also ein guter Anfang. Es reicht jedoch nicht aus, dass alle Lasten in derselben Ebene wirken, damit die Bedingung für die ebene Spannung erfüllt ist, da weiterhin Spannungen in Z-Richtung auftreten können. Hier kommt die Dicke der Platte ins Spiel. Wir wissen, dass Normal- und Schubspannungen an einer freien Oberfläche immer 0 sind. Dies bedeutet, dass die Spannungen auf der Ober- und Unterseite der Platte 0 sein müssen. Da diese Platte sehr dünn ist, kann es über die Plattendicke hinweg keine großen Spannungsschwankungen geben. Dies bedeutet, dass die Spannungen in Z-Richtung überall in der Platte nahe 0 sind. Da die einzigen von 0 verschiedenen Spannungen in der XY-Ebene wirken, gilt die Bedingung für eine ebene Spannung. Natürlich ist es unwahrscheinlich, dass die Spannungen in Z-Richtung in der Realität exakt 0 sind. Die Entscheidung, ob eine ebene Spannungsbedingung anwendbar ist, erfordert immer ein gewisses Maß an technischem Urteilsvermögen. Warum ist die Annahme einer ebenen Spannung nützlich? Wir können dies beantworten, indem wir uns ein Spannungselement in unserer Lochplatte ansehen. Die Spannungen an einem einzelnen Punkt werden durch 6 verschiedene Spannungskomponenten definiert, 3 Normalspannungen und 3 Schubspannungen. Bei ebenen Spannungsbedingungen sind Sigma Z, Tau XZ und Tu YZ gleich 0. Dies bedeutet, dass die 6 Komponenten, die die Spannung an einem Punkt definieren, auf nur 3 Komponenten Sigma X, Sigma Y und Tu XY reduziert werden. Dies ist ein zweidimensionales Problem, das viel einfacher zu lösen ist. Der Spannungstensor für einen dreidimensionalen Fall ist eine 9×9-Matrix. Wenn wir jedoch ebene Spannungsbedingungen betrachten, wird er auf eine viel handlichere 2×2-Matrix reduziert. Betrachten wir 2 weitere Beispiele für Situationen, in denen es angemessen sein könnte, ebene Spannungsbedingungen anzunehmen. Druckbehälter können manchmal unter Verwendung von Annahmen über ebene Spannungen modelliert werden. Die Druckbelastung erzeugt Umfangsspannungen, die sich um den Umfang des Behälters herum orientieren, und Axialspannungen. Wenn die Behälterwand im Vergleich zu ihrem Durchmesser dünn ist, werden die Radialspannungen nahe 0 sein und es gelten ebene Spannungsbedingungen. Die Zähne eines Stirnradgetriebes können manchmal auch unter Verwendung von ebenen Spannungsbedingungen modelliert werden, wenn die Breite des Zahnrads schmal genug ist. Zusammenfassend lässt sich sagen, dass die ebene Spannung eine Vereinfachung ist, mit der man ein dreidimensionales Problem der Festkörpermechanik in ein einfacheres zweidimensionales Problem umwandelt, indem man annimmt, dass die Spannungen in einer Richtung gleich 0 sind. Sie ist normalerweise auf dünne Strukturen anwendbar, die in einer einzigen Ebene belastet werden. Vielen Dank fürs Zuschauen und bleiben Sie dran für weitere Ingenieurvideos.
In this video, we're going to take a look at stress transformation in Mohr's circle. Let's start by reminding ourselves about the stress element. The stress element is a useful way of describing the stresses acting at a single point within a body. In this video, we will consider a 2D stress element, corresponding to a state of plane stress. The normal stresses and shear stresses are shown on the 4 faces of the element. Let's look at a simple example of a beam under axial load. Our stress element is aligned with the direction of the applied load, and so the stress state will be very simple. We will only have a normal stress of sigma x, sigma y, and the shear stresses will be 0. But we might want to rotate our stress element to get the stress state for a specific angle. If there was a weld in our structure, for example, we might want to determine the stresses perpendicular to the weld. Depending on how we choose to orient our stress element, we will get different values for the normal and shear stress components. We can calculate what the normal and shear stresses will be as we rotate our stress element by using the stress transformation equations. The inputs to these equations are the normal and shear stresses at the starting orientation of our stress element, and theta, the angle through which we are rotating the element. Theta is positive for counterclockwise rotation. Let's look at an example of stress transformation for the stress state described by the stress element shown here. As we rotate the stress element, the normal and shear stress components will vary. Once we have rotated the stress element by 180 degrees, we will return to the configuration we started with. It is important to remember that the actual stress state within the large body is not changing when we rotate our stress element. We are just rotating the axes of the coordinate system we are using to visualize the stresses at a single location. We can observe that for certain angles, the normal stress will reach maximum and minimum values, and that these maximum and minimum values are separated by an angle of 90 degrees. This means that when we rotate our stress element such that we have the maximum normal stress on the x face of our element, we always have the minimum normal stress on the y face. Another interesting observation is that when the normal stresses are at their maximum or minimum values, the shear stresses are 0. These faces on which the shear stresses are 0 are called the principal planes, and the corresponding maximum or minimum normal stresses acting on these planes are known as the principal stresses. Principal stresses are very important, so let's recap. They are the maximum and minimum normal stresses acting on our stress element. They always occur when the stress element is rotated such that the shear stresses are 0, as shown here. We denote the maximum and minimum principal stresses using the symbols sigma 1 and sigma 2 respectively. The rotation angle which gives us the principal stresses is denoted using the symbol theta p. Because it is the maximum normal stress at the location of our stress element, being able to calculate sigma 1 can be important for predicting failure. Mohr's circle is a graphical method for easily determining the normal and shear stresses for different orientations of our stress element without having to use the stress transformation equations. Let's see how Mohr's circle is constructed. First, let's draw the horizontal and vertical axes. Normal stress is on the horizontal axis, and shear stress is on the vertical axis. We will plot positive shear stresses in the downwards direction. Next, we plot the stress conditions corresponding to the x face of our stress element by plotting a point with coordinates sigma x, tau xy. Then we plot a point corresponding to the stress conditions on the y face by plotting a point with coordinates sigma y, negative tau xy. The sign convention we use for Mohr's circle is that shear stresses are positive if they tend to rotate the stress element counterclockwise, and are negative if they tend to rotate it clockwise. This is why tau xy is negative on the y face of our element when we draw Mohr's circle. Normal stresses are positive if they are tensile, and negative if they are compressive. The line between these 2 points defines the diameter of our Mohr's circle, which we can now draw. Each point on the circle represents the normal and shear stresses for a certain orientation of our stress element. We can use Mohr's circle to work out some interesting information. We can see visually that the maximum shear stress is equal to the radius of the circle, which we can easily determine either approximately by measuring the distance on paper, or exactly by using the equation for the radius of a circle. We can also determine the principal stresses by looking at where the circle crosses the horizontal axis, as the shear stress is 0 at these locations. The principal stresses can be calculated by taking the x-coordinate of the center of the circle and adding or subtracting the circle radius. We can also use trigonometry to calculate angles on Mohr's circle. For example, we can calculate the angle theta p between our original stress element and the principal planes. An important thing to note is that angles in Mohr's circle are doubled compared to the angle we rotate our stress element by. This is apparent by observing that in Mohr's circle there is a 180-degree angle between the minimum and maximum principal stresses, whereas on our stress element, the angle is 90 degrees. This is why we use the 2 times theta notation on Mohr's circle. Theta is the angle we rotate our stress element by, and 2 times theta is the corresponding angle on Mohr's circle. So far, we have only looked at a 2-dimensional case, but we can extend what we have learned to 3 dimensions. A 3-dimensional stress element looks like this. In 3 dimensions, we have 3 principal stresses, which by convention are numbered from largest to smallest. Mohr's circle in 3 dimensions is made up of 3 different circles, drawn as shown here. All possible combinations of normal and shear stresses for our 3D stress element lie on the boundary of or within this shaded area. I hope this video has helped you better understand stress transformation in Mohr's circle. Please let me know what you think in the comments, and don't forget to subscribe. The typical stress-strain curve for a ductile material, which is obtained by performing a tensile test, looks something like this. But this curve is just an approximation. It doesn't represent the actual stress or strain in the test piece during the tensile test. In this video, we're going to talk about true stress and true strain. In the typical stress-strain curve, stress is defined as the applied force divided by the initial cross-sectional area of the test specimen, and strain is defined as the change in specimen length divided by the initial length. These stress and strain values are actually just approximations of the true stress and strain in the specimen. We call them engineering stress and engineering strain, and denote them using the subscript E. This curve is known as the engineering stress-strain curve. To determine the true stress and strain values, we would need to consider the fact that the dimensions of the specimen change throughout the duration of the test. If we were to measure the true stress and strain, our stress-strain curve would look something like this. You can differentiate a true curve from an engineering curve by noting that the engineering curve drops after necking, whereas the true curve is always increasing. Remember that necking is the rapid reduction in the cross-sectional area of the test piece, which begins when the engineering curve reaches its maximum value, which is the ultimate tensile strength of the material. So, if they do not accurately reflect the true stress and strain in the test specimen, why do engineers commonly use engineering curves instead of true curves? Well, there are 2 main reasons. Firstly, it's quite difficult to measure the instantaneous cross-sectional area during a tensile test. And so, most of the time we just don't have the true stress-strain curves. And secondly, most of the time we are only analyzing or designing things which deform within the elastic region. As you can see here, the engineering and true curves are very similar for small strain values. But for cases where we have large plastic deformation, the difference between the 2 curves becomes significant. This is in large part due to the sudden reduction in the cross-sectional area of the test piece when necking occurs. When assessing cases where we have significant plastic deformation, it becomes important to use the true stress-strain curves. Examples of this might be the analysis of manufacturing processes, or performing finite element analysis, which models large strains. By making a few assumptions, we can calculate the true stress-strain curve based on the engineering curve, and so we can avoid having to measure the instantaneous cross-sectional area during the tensile test. Unlike engineering stress, which is calculated by dividing the applied force by the initial cross-sectional area of the test piece, True stress is calculated by dividing by the instantaneous cross-sectional area at each instant throughout the test. It accounts for the fact that the cross-sectional area of the test piece is changing as the test is performed. We can adjust this equation for true stress by assuming that the volume of the test piece remains constant. This assumption is valid in the elastic region of the stress-strain curve, because any volume changes in the elastic region will be small. And it is valid in the plastic region of the curve, because materials are considered to be incompressible during plastic deformation. I talk more about material incompressibility in my video on Poisson's ratio. If volume remains constant, the product of the instantaneous area and the instantaneous length is equal to the product of the original area and the original length. But it is important to know that this assumption is not valid after necking has occurred, because of the associated change in the cross-sectional area. Beyond necking, we would need to base the true stress on actual measurements of the cross-sectional area. But anyway, we can rearrange this equation so that instantaneous area is on the left-hand side, and then substitute it into our equation for true stress. The definition of engineering strain is that it is the change in length divided by the original length. We can rearrange this equation to the form L divided by L0 minus 1, and we can use this to obtain an equation for true stress, which is a function of the engineering stress and engineering strain, both of which can easily be obtained from a tensile test. Now let's derive an equation for true strain. True strain needs to consider the fact that the original length of the specimen is continuously changing at each instant throughout the duration of the tensile test. We could calculate it by splitting the tensile test into increments and calculating the change in strain at each increment based on the length at the start and end of the increment. In this example, I will consider 3 increments. The increments can then be summed up to calculate the true strain at the end of increment 3, for example. Instead of doing this manually with large increment sizes, this approach can be defined mathematically using integration, like this. By remembering that the integral of 1 over x is ln of x plus c, we end up with this equation, which can be rearranged to be a function of the engineering strain. Because of the form of this equation, true strain is also known as logarithmic strain, or natural strain. I hope this has helped explain the differences between engineering and true stress strain curves. Thanks for watching, and remember to hit the subscribe button and the bell to be notified about future videos. Torsion is the twisting of an object caused by a moment acting about the object's longitudinal axis. It is a type of deformation. A moment which tends to cause twisting is called torque. A common example of an object subjected to torsion is the transmission shaft, which is used to transmit power by rotation. This could be the drive shaft and axles, used to transmit power from the engine of a car to the wheels, for example, or the shafts used to transmit power from the blades of a wind turbine to its generators. Let's explore what happens when we apply torque to a circular bar. We can see that the applied torque causes the bar to deform by twisting. An interesting thing we can observe is that individual cross-sections of the bar do not get distorted by the twisting. We can imagine that the bar is made up of multiple individual discs, which rotate relative to each other when the torque is applied, but do not deform. This is only true because the cross-section of the bar is axis symmetric. A bar with a rectangular cross-section is not axis symmetric, and so torsion results in warping of the bar cross-sections. This warping is complex, so in this video we will keep things simple and only consider torsion as it relates to circular bars. Let's fix our bar at one end, and track how a line between point A and point B deforms as we apply a torque to the other end. The applied torque causes the free end of the bar to rotate by an angle phi. This is called the angle of twist. It varies linearly from 0 at the fixed end of the bar to phi at the free end of the bar. We can calculate the angle of twist using this equation. It is a function of 4 parameters: the length of the bar L, the applied torque T, the shear modulus G, which is material property, and J, which is the polar moment of inertia. So, what is the polar moment of inertia? It defines the resistance of a cross-section to torsional deformation, due only to the shape of the cross-section. The polar moment of inertia for a hollow bar, with an outer radius RO and an inner radius RI, can be calculated using this equation. Setting the inner radius to 0 gives us the equation for a solid bar. One neat thing about the equation for the angle of twist is that it gives us a way to determine a material's shear modulus G experimentally. If we apply a known torque to a bar of known length and cross-section and measure the resulting angle of twist, we can use that information to calculate the material's shear modulus G. Torsion generates stresses and strains within the bar, which we need to be able to calculate so that we can make sure our bar won't fail. To figure out how to calculate these stresses and strains, we can start by observing how a small rectangular element on the surface of our bar deforms. The element is initially rectangular, but when the torque is applied, it gets distorted. Let's take a closer look. Because the bar is axis symmetric, we know that individual cross-sections will rotate but won't get distorted. So the sides CF and DE of the element will only move vertically along the lines shown here. After the torque is applied, the angles of the element are no longer 90-degree angles. This gives rise to a shear strain, which corresponds to the angle you can see here. We can calculate the shear strain by considering only the geometry of the bar in the deformation. It corresponds to this angle between AB and AB'. We can use trigonometry to derive an equation for shear strain. For small angles, gamma will be approximately equal to the tangent of gamma, which makes it equal to the length BB' divided by the length AB. AB is the length L of the bar. We can calculate the length BB' by realizing that it is the arc length of a circle with a radius r, covering an angle equal to the angle of twist theta. So the shear strain is equal to the radius of the bar multiplied by the angle of twist divided by the length of the bar. This is actually only an equation for the shear strain on the surface of the bar. But what about inside it? It turns out that the shear strains increase linearly with the distance from the center of the cross-section. So if we define ρ as the radial distance from the center of the cross-section, we can replace r in this equation with ρ, to give us an equation we can use to calculate shear strain due to torsion at any point within the bar. That's shear strains covered. But what about shear stresses? Like the shear strains, shear stresses increase linearly with the distance from the center of the cross-section, with the maximum shear stress occurring on the outer surface, as you can see here. This is true for a solid bar, but also for a hollow bar. This is useful to know because it means that hollow bars are way more efficient at carrying torsional loads, since the central part of a solid bar is only resisting a small part of the total load. Let's consider a small element within our cross-section that has an area equal to dA and is located at a distance ρ from the center of the cross-section. The internal force acting on this element is equal to its area, dA, multiplied by the shear stress τ. We can use this information to work out an equation for calculating the shear stresses. The moments caused by the internal forces acting on all of the elements within the cross-section must sum up to be equal to the torque T. Otherwise, equilibrium is not maintained. We can represent that mathematically by this integral. We know that the quantity τ divided by ρ is a constant. because the shear stress varies linearly with the distance from the center of the cross-section. So we can rearrange the terms and move tau over rho out of the integral. It turns out that the integral we now have on the right is actually the definition of the polar moment of inertia, so we can replace it with the letter J, and we can rearrange this to get an equation for shear stress. The shear stress is a function of the torque T, the distance rho from the center of the cross-section, and the polar moment of inertia J. It's quite a simple equation. So we now have equations that allow us to calculate the shear strains and shear stresses. We also have the equation for angle of twist that we talked about earlier. These three equations tell us everything we need to know about a circular bar which is under torsion. So far, we have only talked about a uniform bar fixed at one end with a single applied torque, but shafts are often loaded by multiple torques. This shaft, for example, which is supported by bearings at both ends, is driven by a gear at point B, and in turn drives two gears at points A and C. It is loaded by three torques. Before we can use the equations for shear stress, shear strain, and angle of twist that we just developed, we need to figure out the internal torque at each location along the shaft. The process for doing this is similar to calculating the shear force along a beam, which I covered in a separate video. First, we draw a free body diagram. Then we make imaginary cuts and use the concept of equilibrium to determine the internal torque at different locations along the shaft. This will give us an internal torque diagram that looks something like this. The maximum shear stress will occur in the section of the shaft with the largest internal torque, and can easily be calculated using the equation we derived earlier. I want to end the video by talking about failure due to pure torsion. If we have two bars, one made of a ductile material and one made of a brittle material, and we apply the same torque to both bars, we will observe that they fail differently. The ductile bar fails at an angle perpendicular to its axis, but the brittle bar fails at a 45-degree angle to its axis. We can explain this by remembering that ductile materials tend to fail in shear, and so fracture along the plane of maximum shear stress. But brittle materials are weaker in tension than in shear, and so tend to fracture along the plane of maximum tensile stress. Mohr's circle for pure torsion looks like this. We can see that when our stress element is oriented this way, the shear stresses are at their maximum values, and we have no normal stresses. There is a 90-degree angle on Mohr's circle between maximum shear stress and maximum normal stress, which means that normal stresses are at a maximum when our stress element is rotated by an angle of 45 degrees. This explains why brittle and ductile materials fail in different ways due to pure torsion. That's it for now. Thanks for watching, and don't forget to subscribe if you haven't already. Thanks to CuriosityStream for sponsoring this video. When a bar is loaded in uniaxial tension, it will fail when the normal stress in the bar exceeds the yield or tensile strength of the material. And if it's loaded in compression, it will fail by crushing when the compressive strength of the material is exceeded. But there's an additional way the bar can fail when in compression, which is by buckling. Buckling is a loss of stability that occurs when the applied compressive load reaches a certain critical value, causing a change in the shape of the bar. An initially straight member will buckle suddenly, producing large displacements. This doesn't always result in yielding or fracture of the material, but buckling is still considered to be a failure mode, since the buckled structure can no longer support a load in the way it was designed to. The most simple example of a structure at risk of buckling is a column. But individual members and trusses and frames can also be loaded in compression, and so are at risk of buckling. There are other less obvious examples too. When railway tracks heat up on a hot day, the steel the tracks are made of tends to expand. But expansion in the axial direction is prevented, and so a compressive axial force builds up, which can lead to buckling. A very similar issue can occur in subsea pipelines that carry hot product. The compression that builds up due to the thermal expansion of the pipe steel can cause the pipeline to buckle on the seabed. Buckling can clearly lead to catastrophic failure, so how do we take it into account in engineering design and analysis? To answer this question, we need to travel back to the mid-18th century. In 1744, the mathematician Leonhard Euler published a book in which he laid out a new method for analyzing functions, called the calculus of variations. To illustrate how this new method could be applied, Euler included in an appendix the derivation of an equation for the axial load that will cause a column to buckle. This is the Euler buckling formula, a simple equation that engineers continue to use almost 300 years later to design columns and other members that are loaded in pure compression. It's probably the oldest engineering design equation that's still in regular use. The critical load at which a column will start buckling depends on only three parameters: the Young's modulus of the column material, the area moment of inertia of its cross-section, and its length. It doesn't depend on the strength of the material at all. This form of the equation is valid for a column that is pinned at both ends, meaning that the ends can rotate but can't translate horizontally. So a 2-meter tall steel column that has a circular cross-section with a radius of 40 millimeters would be expected to be able to support a load of around 1,000 kilonewtons before buckling, not including any safety factors. This assumes an idealized, perfectly straight column. At the critical buckling load, any small perturbation, whether it's a lateral force or a small imperfection, will cause the column to bend. If the cross-section has a smaller area moment of inertia about a particular axis, the column will buckle in that direction, and the smaller value of I must be used to calculate the critical buckling load. If the end conditions change so that the column is fixed at one end and free at the other, it will clearly only be able to support a much smaller load before buckling, and the buckled shape is different. We can easily modify Euler's formula to account for different end conditions by introducing the concept of an effective length. The effective length can be defined as the distance between inflection points on the deflected shape. The column that's pinned at both ends has an effective length equal to the column length. But for a column that's free at the top and fully fixed at the bottom, the distance between inflection points is twice the column length. Here are a few other common end conditions and the associated effective lengths. We can replace the column length in Euler's formula with the effective length to make the equation applicable for all of these end conditions. Or we can keep the column length and add in an effective length factor k. End conditions clearly make a huge difference to the critical buckling load and must be considered very carefully. In real-life applications, it isn't always clear which effective lengths should be used, and the amount of restraint at the ends will depend on the stiffness of the adjacent members. Design codes often provide guidance on conservative assumptions that can be used for these scenarios. Even without knowing anything about Euler's formula, it's intuitively quite obvious that slender columns are at much greater risk of buckling than stocky ones. It's why you would never design a truss structure with long compressive members like this. This member is under compression, and since it's so long and thin, it's at risk of buckling. Members of a truss that are in compression are sometimes designed to be thicker than those in tension to reduce the risk of buckling. And long compressive members are prevented from buckling by the use of bracing members. Euler's formula confirms this intuition about slender columns. The length term is squared, and so doubling the length of a column means that it can only support a quarter of the weight before buckling. To better understand the effect of slenderness, it's useful to introduce a non-dimensional parameter called the slenderness ratio. First, let's divide the critical load by the cross-sectional area to obtain a critical stress. Then, if we define the radius of gyration r of the column as the square root of I divided by A, we can write the equation for critical stress in a new form. The term L over R is the slenderness ratio. Let's take a look at how the Euler critical buckling stress varies with the slenderness ratio. Very slender columns have a large slenderness ratio and a very low critical buckling stress. For stocky columns with low slenderness ratios, the critical buckling stress will be very large. If we draw the compressive yield strength of the column material on this graph, we can see that for these slenderness ratios, the strength of the material will be exceeded before the buckling limit is reached. This means we can define two distinct regions, where beams fail by crushing because the stress in the column exceeds the material yield strength, and where they fail due to buckling. The limiting slenderness ratio depends on the material Young's modulus and yield strength. For steel columns, the limiting slenderness ratio is around 90. But this curve only represents the theoretical behavior of columns. If we plot buckling stresses determined experimentally for real columns, we can see it doesn't exactly match the theoretical behavior. In particular, the transition between plastic failure and elastic buckling failure is much more gradual. This is because for columns in this transition range, buckling is actually a complex combination of these two failure modes. This is called inelastic buckling, and the theoretical behavior can be modeled using methods like Engesser's theory or Shanley's theory. There's a much better correlation between the test data and Euler's formula for very slender columns. But even for these columns, there are some limitations to Euler's formula that the engineer needs to be aware of. One of these limitations is that the formula assumes that the applied load acts exactly through the centroid of the column cross-section. But the applied load will always be slightly offset from the centroid, even if it's by only a very small amount. This eccentricity introduces a moment that acts in addition to the axial load, which reduces the critical buckling stress and significantly changes how buckling occurs. If the load is applied at the centroid of the cross-section, the force displacement curve looks like this. There is no displacement until the critical buckling load is reached, at which point the displacement suddenly becomes very large. But in the case of an eccentric load, the additional moment causes the column to bend as soon as the load is applied. Because of the bending, the stress in the column isn't uniform. The maximum compressive stress occurs on the inner surface halfway up the column, and can be calculated using the secant formula. Another limitation of Euler's formula is that it assumes that the column is perfectly straight before the load is applied. But real columns contain imperfections, and however small they may be, these can reduce the critical buckling load. Since imperfections introduce bending, they have a similar effect to an eccentric load, and so can be modeled in the same way. Euler's formula and the secant formula also assume that displacements are small. If displacements are large, the moment acting on the column will change significantly throughout the deformation, introducing significant geometric nonlinearity. In structural analysis, this is called the p-delta effect. Most design codes deal with these limitations of Euler's formula and the complexities of inelastic buckling by providing design curves that engineers can use directly to design columns. These curves are calibrated using experimental data and are applied in combination with suitable safety factors to ensure a safe design. Euler's formula is used to calculate the critical buckling load for a column where the displacement occurs by bending. This is called flexural buckling. But members can buckle in other ways too, and these also need to be checked during design. Columns with thin-walled open cross-sections tend to have low torsional stiffness. Under certain conditions, these columns can buckle by twisting, called torsional buckling, or by a combination of twisting and bending, called torsional flexural buckling. So far, we've considered buckling of columns and other straight members, like those you might find in a truss or a frame. But thin plates and shells like those you would find in a storage tank are also susceptible to buckling. Buckling in these types of structures is even more sensitive to the presence of imperfections than it is in columns, and the effects are more difficult to predict. And so, although analytical equations do exist to calculate critical buckling loads for plates and shells, they're usually considered to provide an upper limit on the buckling load. Detailed nonlinear analysis using the finite element method is often required for this type of structure. We've seen that slender columns can buckle when compressive loads act on them. But what about the effect of gravity? Is it possible that a column could be built tall enough that it would buckle because of nothing other than its own weight? This is a problem that even Euler struggled with. But since it didn't really fit into this introduction to buckling, I've covered it in a short companion video that you can watch right now over on Nebula. Nebula is a streaming platform that I've been building with a group of independent educational creators. It's a place where you can watch our videos completely ad-free, but also get access to exclusive Nebula originals and bonus content from amazing creators like Mustard and Real Engineering. The best way to get Nebula is through our bundle deal with this video's sponsor, CuriosityStream. CuriosityStream is a huge streaming service for documentaries that has thousands of titles for you to choose from. No matter what you're interested in, you'll find something special to watch on CuriosityStream. So after you've watched the self-buckling video on Nebula, why not start The World of Bridges on CuriosityStream, a series that covers the history, construction, and maintenance of famous bridges around the world. Or check out Juice, a film that explores the issues that revolve around access to electricity. The bundle deal gives you a 26% discount on the CuriosityStream annual plan and full access to Nebula for free, but you can only get it by signing up using this link. So to watch the companion video on self-buckling over on Nebula, and get access to thousands of documentaries on CuriosityStream, all for less than $15 a year. Head over to curiositystream.com/efficientengineer or click the button on screen now. Signing up is a great way to support this channel. And that's it for this introduction to buckling. Thanks for watching. Components which are subjected to loading which varies with time can fail at stresses well below the material's ultimate strength. This is known as fatigue failure, and it accounts for the vast majority of mechanical engineering failures worldwide. The bolts in an office chair, the crank arm on your bicycle, and pressurized oil pipelines are just a few examples of components which are subjected to time-varying loads and may be at risk of fatigue failure. Fatigue failure occurs due to the formation and propagation of cracks. It is a three-stage process. The first stage is crack formation. This usually occurs at free surfaces and at stress concentrations. In stage 2, the crack grows in size. And in stage 3, after the crack has grown to a critical size, fracture occurs. So how can we figure out whether a component is likely to fail due to fatigue? One common approach is to run fatigue tests by subjecting a component or test piece to a large number of constant amplitude stress cycles and counting the number of cycles until it fractures. If we repeat this test a large number of times with different applied stress ranges, we can plot the results on a graph, with the number of cycles to failure n on the horizontal axis and the applied stress range s on the vertical axis. Because the number of cycles to failure can be very large, a log scale is usually used for the horizontal axis. By fitting a curve to the data points, we obtain what is known as an SN curve. The SN curve allows you to calculate the number of cycles until a component is likely to fail for a given stress range. For example, if we have a stress range of 100 MPa or 15 KSI, this SN curve tells us that the number of cycles to failure is 500,000. If we know that our component is subjected to 1 cycle per minute, we could predict that our component will fail due to fatigue after approximately 1 year. Fortunately, we don't have to perform these time-consuming fatigue tests ourselves. SN curves for many different materials are already published in different engineering codes. For some materials, and in particular for ferrous materials, it is important to note that the SN curve at a very large number of cycles becomes a horizontal line. This is known as the endurance limit. Theoretically, the component could be cycled at stress ranges below this level forever, and it will never fail due to fatigue. This makes the endurance limit an important fatigue design parameter. It is common to differentiate between high cycle and low cycle fatigue. High cycle fatigue occurs when the applied cyclical stresses are low, and failure occurs after a very large number of cycles, typically more than 10,000 cycles. Because the stresses are low, we are only dealing with elastic deformation. Low cycle fatigue involves higher applied cyclical stresses, and failure occurs after fewer cycles. Because the stresses involved are above the material's yield stress, both elastic and plastic deformation occur. In these cases, a strain-based approach, using for example the Coffin-Manson relation, is usually preferred to the SN curve approach. If we return to the data from our fatigue tests, we can see that there is a large amount of variability in the data. This is typical for fatigue tests, even when identical test pieces are used. If we use a best fit SN curve, as we have done here, there is a significant possibility that our component will fail at a much smaller number of cycles than the curve predicts. This test piece, for example, failed at a much lower number of cycles than predicted by our SN curve. For this reason, SN curves published in engineering codes are normally shifted downwards by a certain number of standard deviations to give a reduced probability of failure. Here, by shifting the mean curve down on the vertical axis by 2 standard deviations, we have reduced the probability of failure from 50 to 1%. Fatigue tests are usually run for the constant amplitude fully reversing cycles you can see here. The same stress magnitude is applied in tension and in compression. Let's define a few terms. The stress range is defined as the difference between the maximum and minimum stresses. The stress amplitude is defined as half of the stress range. The mean stress is the average of the maximum and minimum stresses. In this case, the mean stress is 0. But this is only one very specific type of loading. In some cases, we might have a mean stress which is not equal to 0, as shown here. This mean stress will have an effect on the fatigue life. A tensile mean stress will typically result in a shorter fatigue life. One way to account for a tensile mean stress is to use SN curves derived for specific values of mean stress. But these are often not available, or would be time-consuming to obtain. Another approach is to use the Goodman diagram, which adjusts the endurance limit to account for a mean stress. Let's see how it works. On a Goodman diagram, the mean stress is shown on the horizontal axis, and the stress amplitude is shown on the vertical axis. A straight line is drawn between the endurance limit, at a mean stress of 0, and the material ultimate tensile strength, at a stress amplitude of 0. If our cyclic loading conditions are located below the Goodman line, our component will be safe from fatigue failure. There are a few different variations of this diagram, as you can see here. This approach can only be used to determine whether a component will have an infinite life. It doesn't allow us to calculate a fatigue life. In many real-world cases, the applied loading is likely to be far more complex than what we have considered so far. We can use techniques like the rainflow counting method to simplify a complex stress spectrum into a number of simpler, constant amplitude cycles. Miner's rule allows us to account for the cumulative damage caused by each of these different constant amplitude stress ranges. It calculates the damage fraction D as the sum of the fatigue damage contributions for each stress range. The individual contributions are calculated by dividing the number of cycles by the number of cycles to failure for that stress range. The damage contributions from all stress ranges are then summed. If the total sum damage fraction is greater than 1, fatigue failure is considered to have occurred. In this example, the damage fraction D sums to 0.94. This is less than 1, and so fatigue failure has not occurred. If the structure we are assessing contains an existing crack, the SN approach is not suitable for determining the fatigue life. If the dimensions of the crack are known, we can instead determine the fatigue life using a linear elastic fracture mechanics approach. This involves calculating a critical crack size, which would result in fracture, and using a crack growth law to calculate the time required for the crack to grow to this critical size. But that's enough about fatigue for now. Stay tuned for more engineering videos. Thanks to Brilliant for sponsoring this video. Beams are used to carry loads in a whole range of different structures, and it's important for engineers to be able to predict how much a beam will deflect when loads are applied to it. Allow a beam to deflect too much, and it could cause damage to other parts of the structure, feel unsafe to the user, or fail to meet its intended function, even if stresses in the beam are low and there's no risk of failure. Construction codes typically define what the maximum allowable deflection is, and so it's up to the engineer to figure out how much the beam will deflect. There are quite a few different approaches that can be used to do this. I'll cover 5 of the more common methods in this video. All of these methods make the same important assumption, which is that deflections are small and stresses remain in the elastic region. For this reason, the deformed shape of the beam is called the elastic curve. We can define x as the distance along the axis of the undeformed beam, and y as the vertical deflection of the beam. The objective is to figure out how y varies along the length of the beam. We will assume that there's no displacement along the x-axis. We're also interested in the angle of rotation of the beam, theta. Let's take a closer look at the angle. We can define the slope of the beam as dy divided by dx. Since we're limiting ourselves to scenarios where deflections are small, we can apply the small angle approximation, and so we can assume that the angle of rotation is equal to the slope of the beam. In other words, the angle of rotation is equal to the first derivative of y with respect to x. We can start thinking about how beams deflect under load by reviewing the moment curvature equation. It allows us to calculate the curvature of a beam for a given bending moment. M is the bending moment, R is the radius of curvature of the deformed shape, and EI is the flexural rigidity of the beam, which defines how much the beam will resist bending due to the stiffness of its material and due to its cross-sectional shape. The term 1 over R is the curvature of the beam. The moment curvature equation is the first step towards being able to calculate the deflection of a beam, since it gives us information about how the beam will deform for an applied bending moment. It turns out there's a mathematical equation that can be used to calculate the curvature at any point along a curve. We can combine this with the moment curvature equation to get an expression that relates the deflection of the beam and the bending moment along it. But this equation is still quite complicated, so let's try and simplify it. Since we're limiting ourselves to elastic deformation and assuming that the slope of the elastic curve is small, the dy over dx term will be small. And since it's squared, it will be even smaller, and so can be neglected. This gives us a much simpler differential equation defining the deflection of the beam. All we need to do to get an expression for the deflection along a beam is integrate the equation twice. This is called the double integration method. It's easiest to understand how the method works using an example. Here we have a cantilever with a load applied at the end. We'll start by drawing the free body diagram and applying equilibrium to determine the reaction forces. Next, we want to calculate the bending moment along the beam. If we draw a free body diagram of a slice of the beam, we can see that as we move along the beam, the bending moment increases linearly with the distance from the concentrated force P. So the bending moment M is equal to minus P times X. We can insert this expression for M into the deflection differential equation and apply the double integration method to figure out how the beam will deflect. E and I are constant along the length of the beam, so we can pull them outside of the integral, and then integrate the equation for M with respect to X. Remember that whenever you integrate, you need to add a constant of integration at the end. We'll call it C1. It's an unknown for now. Then we integrate a second time, remembering to add a second constant of integration. And so we now have an equation that defines the deflection y of the beam. The only problem is that we have two unknown constants. Fortunately, we can use what we know about the deflection and the slope of the beam at the support to calculate C1 and C2. At the fixed end, the beam cannot rotate, so the slope dy over dx must be equal to 0. This allows us to calculate C1. And at the same location, the deflection y must also be 0, which gives us C2. And so, we've solved the deflection curve for this beam. In this case, it's obvious that the maximum deflection will occur at the end of the beam. For cases where the location of maximum deflection is less obvious, like for this simply supported beam, we can observe that the slope of the beam will be 0 at the location of maximum deflection. So by setting the slope equation to be equal to 0, we can figure out the location of y max. Boundary conditions are key to applying the double integration method. We just saw that at a fixed support, the displacement and the slope must both be 0. At a pinned support, the beam is free to rotate, so the slope can be non-zero, and only the boundary condition for the displacement applies. The same is true for a roller support, which is also free to rotate. The double integration method is quite easy to apply, but even for some quite simple configurations like this one, the bending moment won't be defined by a single expression along the full length of the beam. To apply the double integration method in situations like this, we need to split the beam into sections and determine separate expressions for the bending moment in each section. We then apply the double integration method to the different sections, and we end up with a lot of different constants of integration. By considering the boundary conditions at the supports, we can calculate some of these constants. To solve the remaining constants, we need to consider what's called the continuity condition between the different sections of the beam. Since the beam remains continuous across the transition between these two sections, the displacement and slope must be the same at the right of section 1 and at the left of section 2. This gives us a system of equations we can solve to determine the remaining constants of integration. Having to split the beam into sections and solve a system of equations complicates things and makes it more difficult to solve the deflections of the beam, particularly for cases where the beam needs to be split into a large number of sections. Fortunately, there's a powerful mathematical trick that allows us to define a bending moment profile like this one using a single expression, so that we can apply the double integration method without having to split the beam into sections. It uses singularity functions to make solving this type of beam much easier. They are defined using this special notation and follow specific rules. When the expression inside the bracket gives a positive number, the output is the expression, but when it is negative, the output is 0. These are called Macaulay brackets, and applying them to calculate the deflection of beams is called Macaulay's method. Their behavior allows us to essentially turn different terms in the bending moment equation on and off as we move along a beam. We can work through the beam we looked at earlier to understand how. Let's see how the bending moment changes as we move along the beam. In the first half of the beam, only the reaction force contributes to the bending moment, and the moment arm is equal to x. But once we get past halfway, we need to include the effect of the concentrated load as well. And so the bending moment expression has to include an additional term. The moment arm is equal to x minus half the length of the beam. If we replace the brackets in this expression with Macaulay brackets, the second term in the expression will be switched off in the first half of the beam, since x minus L over 2 will give a negative number. And so this expression using Macaulay brackets defines the bending moment along the entire length of the beam. The same thing works for distributed loads, although it's slightly different. When using Macaulay brackets for a uniformly distributed load, the bracket has to appear twice, once in the magnitude of the load and once in the moment arm. The moment arm is the distance to the center of the distributed load, so is equal to the length over which the load is applied, divided by 2. And so we get this expression, where the Macaulay bracket is squared, and the distributed load is divided by 2. This expression is only valid if the distributed load extends all the way to the end of the beam. If it doesn't, we have to adjust the expression to balance the part of the load that's missing. Here's how you can apply Macaulay brackets for a few other load types. Macaulay brackets also have special rules for integration. They are integrated in a similar way to polynomial functions, like this, which makes it easy to apply the double integration method when using them. Let's go back to our beam with a concentrated load and solve the deflections using Macaulay's method. Since we have a single expression that defines m along the full length of the beam, we no longer need to split the beam into sections to solve it, and we can just apply the double integration method as we normally would. The double integration method can be quite time-consuming to apply, even when using Macaulay's method. To save us from having to go through the integration process every time we want to calculate the deflection of a beam, reference texts often include tables which list the deflection equations for a set of typical load and support configurations. This is more powerful than it might seem at first glance, because the principle of superposition can be used to apply this small set of solutions to a much wider range of problems. It allows us to combine different load configurations on top of one another, and to calculate the overall deflection caused by the combined loading by summing up the contribution of each load to the total deflection. This is a really powerful technique that's not just used for the analysis of beams, but also more widely in structural analysis. For the superposition method to be applicable, deflections must vary linearly with the applied loads. And deflections need to be small, since large deflections could mean that the applied loads don't act independently. Sometimes when analyzing a beam, we might only be interested in calculating the angle of rotation or the displacement at a single location, instead of along the entire length of the beam. There's another method we can use for cases like this, which is called the moment area method, because it's based on the area under the bending moment diagram. If we take 2 points, 1 and 2, and we integrate both sides of the deflection differential equation between those 2 points, we end up with this equation. The term on the left is the change in angle between both points, which we can visualize by extending lines tangent to the elastic curve at the 2 points. And the term on the right is just the area under the bending moment diagram between both points, A, divided by the flexural rigidity, EI, assuming that both E and I are constant along the length of the beam. So, to calculate the change in angle between 2 points along the elastic curve, all we have to do is divide the area under the bending moment diagram between the 2 points by EI. This is the first moment area theorem. If we rewind and multiply both sides of the deflection differential equation by x before integrating, we can get another useful equation. This time, the integration is a bit more complicated, since we need to use integration by parts. But we end up with this expression, which is the second moment area theorem. It tells us that the vertical distance between point 2 and the tangent line at point 1 is equal to the first moment of the area of the bending moment diagram, divided by EI. The first moment of area is just the area under the diagram, multiplied by the horizontal distance from point 2 to the centroid of the area. This vertical distance is called the tangential deviation. It might not seem that useful, since it doesn't directly give us the deflection at point 2. But if we calculate the tangential deviation at the other end of the beam, we can then use trigonometry to figure out the actual deflection at point 2. The moment area method is particularly useful when there's a point along the beam where we know that the slope of the elastic curve will be equal to 0, since in that case, calculating the tangential deviation gives us the deflection directly. This is why the moment area method is often applied for cantilever problems. Let's look at an example. We're interested in the deflection and angle of rotation at the free end. So let's define point 1 at the fixed support and point 2 at the free end. Because the angle and deflection are 0 at point 1, the moment area method will give us the deflection and angle at point 2 directly. We can define x as the horizontal distance from the free end and draw the bending moment diagram. To apply the moment area method, we need to calculate the area under the bending moment diagram between points 1 and 2, and the distance between point 2 and the centroid of the area. It's easy to do this by splitting the diagram into 2 triangles and a rectangle. The areas are easy to calculate. And for the centroids, we just need to remember that the centroid of a right-angled triangle is 1/3 of the way down and 1/3 of the way across from the right angle. Then we can just plug the numbers into the first and second theorems to calculate the angle and deflection at point 2. There's one last approach to analyzing the deflection of beams that I'd like to cover, which is an energy approach that uses the concept of strain energy. When a body is deformed elastically, energy is stored within it in the form of strain energy. For a beam deformed by bending, the strain energy is a function of the bending moment, and it can be calculated using this equation. It's common to neglect any shear deformation and assume all of the strain energy is coming from pure bending. Castigliano's theorem states that the deflection at the location of an applied load along the line of action of the load is equal to the partial derivative of the strain energy with respect to that load. The deflection can be a displacement or an angle of rotation. Because the bending moment term is squared in the strain energy equation, it's usually easier to move the partial derivative inside of the integral, like this. Let's look at an example. The bending moment along the beam shown here is defined by this expression. We can calculate the partial derivative of m with respect to p. Using Castigliano's theorem and integrating between 0 and L, we get an expression for the displacement at point A. The powerful thing about Castigliano's theorem is that the load we consider doesn't even have to be a real load. If we want to determine deflections at a location where no load is applied, we can just apply a fictitious force. We include the fictitious force in the bending moment equation, and then once we've calculated the partial derivative of the strain energy with respect to that force, we can set it to 0 to obtain an equation for the deflection at that location. The fictitious load can be either a moment or a force. Applying a moment allows us to calculate the angle of rotation, and applying a force allows us to calculate the deflection y of the beam. Applying a fictitious moment at point A allows us to calculate the angle of rotation at that point. This time, we take the partial derivative of m with respect to ma. Once we have an expression for the angle of rotation, we can set the fictitious moment ma to be equal to 0. Although it might be slightly more difficult to conceptualize than the other methods we've looked at, Castigliano's theorem can be very powerful when applied properly, and it has uses that extend well beyond the analysis of beams. With experience, you'll be able to select the method that will be easiest or most appropriate to apply, based on the specifics of the situation you are analyzing. But one inescapable fact when it comes to applying any of these methods is that they rely heavily on having a solid understanding of calculus. Mastering the fundamentals of calculus is the best way to make beam deflection problems feel much less daunting. And this video's sponsor, Brilliant, is a math and science learning platform that will help you do exactly that. It has all of the steps covered, from the basics of what differentiation and integration actually are, all the way up to complex topics like partial differential equations and Laplace transforms. The thing I love most about Brilliant is how easy it makes it to learn. Topics that would otherwise be difficult to absorb are creatively broken up into bite-sized chunks, and Brilliant guides you through them, challenging you to learn actively with loads of fun interactive problems to solve along the way. You can really set yourself up for a successful career in engineering by mastering the fundamentals of calculus, and Brilliant is a great way to do it. So, to take the first step towards calculus mastery and support this channel at the same time, head over to brilliant.org/efficientengineer or click the link in the description and sign up for free. The first 200 people to sign up using that link will get 20% off the annual premium subscription. And that's it for this look at the deflection of beams. Thanks for watching. If we apply a load to a beam, it will deform by bending. This generates internal stresses, which can be represented by a shear force acting in the vertical direction, and a bending moment. The shear force is the resultant of vertical shear stresses, which act parallel to the cross-section, and the bending moment is the resultant of normal stresses, called bending stresses, which act perpendicular to the cross-section. It's important to have a good understanding of these stresses because any design or analysis of a beam will involve calculating them. Let's look at bending stresses first. To keep things simple, we'll consider a case of pure bending. A section of a beam is said to be in a state of pure bending when the shear force along it is equal to 0, and so there is a constant bending moment along its length, like there is for this beam loaded by 2 moments. We also have a case of pure bending over the middle section of this beam, where the bending moment is constant. Let's look at how a beam deflects when it has a constant bending moment along its length. If we imagine the beam as a collection of very small fibers, as the beam deflects, the fibers at the top of the beam get shorter, meaning that they are in compression, and those at the bottom of the beam get longer, so they are in tension. Somewhere between the top and the bottom of the cross-section, there will be a surface containing fibers which stay the exact same length. This is called the neutral surface. It passes through the centroid of the cross-section. When looking at the beam in 2 dimensions, we refer to it as the neutral axis. Let's try and quantify the bending stresses that develop within the beam to resist these applied moments. First, let's calculate the strains in the beam. This can be done quite easily just by considering the geometry of the deformation. Let's watch how a fiber at the neutral axis between points A and B and a fiber between points C and D located at a distance y from the neutral axis deform. Since this is a case of pure bending, we can see that the fibers bend into a perfectly circular arc. We'll call the center of the circle O. Before any deformation, the fibers are all the same length. After the deformation, the length of the neutral axis has stayed the same, but the length of the fiber between points C and D has increased. If theta is the angle of the arc and r is the radius of the arc to the neutral axis, we can calculate the length of the arc between A and B, like this, and we can calculate the length of the arc between C and D in the same way. Strain is defined as the change in length divided by the original length, and so we can derive an equation for bending strain at any distance y from the neutral axis. We define the distance y as being positive downwards, and so this equation will give us a positive strain for the bottom of the cross-section, which is in tension. Sometimes you'll see this equation written with a minus sign, but that's because y was defined as being positive upwards. If we assume that stresses remain within the elastic region of the stress-strain curve, we can then apply Hooke's law for uniaxial stress to calculate the bending stresses. This gives us the equation for bending stress as a function of the radius of curvature, r, of the deformation. But what we're really interested in is how the bending moment, m, affects the bending stress. If we make an imaginary cut through the beam, we can expose the internal bending stresses, represented here as a few discrete forces. The resultant moment of these internal forces must be equal to the bending moment m, and so we can calculate m by integration, like this. Now we can plug in the equation for bending stress we just derived. When rearranged into this form, we can notice that the integral on the right is the definition of the area moment of inertia. This parameter, which I've covered in detail in a separate video, defines the resistance of a cross-section to bending due to its shape and is denoted using the letter I. We can combine this equation for the bending moment with the bending stress equation to obtain what is known as the flexure formula. So what does it tell us? Bending stress increases linearly as the bending moment and the distance from the neutral axis increase, and it decreases as the area moment of inertia increases. The maximum stress occurs at the fibers furthest from the neutral axis. The term I over y max depends only on the geometry of the cross-section, and so it is called the section modulus, and is denoted using the letter S. You will often see the section modulus listed for a range of common beam cross-sections in reference texts. The I-beam is a commonly used cross-section because it has a large area moment of inertia, which results in lower stresses. Here's how the bending stresses are distributed over an I-beam cross-section. They are zero at the neutral axis and reach a maximum at the outside surfaces of the flanges. For a T-section, the neutral axis is shifted upwards, and so the bending stress distribution looks like this. So we've established how to calculate the bending stresses, which are normal stresses, for a case of pure bending. Most of the time, we won't have pure bending, as there will also be a shear force acting on the beam cross-section, like the beam we saw at the start of the video. It turns out that the presence of a shear force doesn't normally significantly affect the bending stresses, and so, luckily, we can consider the flexure formula we derived earlier for pure bending to be valid for a more general case of bending. The shear force V is the resultant of shear stresses, which act vertically, parallel to the cross-section. We denote the shear stresses using the Greek letter tau. To maintain equilibrium, these vertical shear stresses have complementary horizontal shear stresses, which act between horizontal layers of the beam. One way to visualize these horizontal stresses is to consider a beam made up of several planks of wood. When a load is applied, there is a tendency for the planks to slide relative to one another. Now let's glue the planks together. When the load is applied, the planks cannot slide, and so horizontal stresses develop between them. If these shear stresses are larger than the shear strength of the glue bond, the glue will fail. These horizontal shear stresses don't exist if we apply a moment instead of a force, because that gives us a state of pure bending, and so there is no tendency for the planks to slide relative to one another. The presence of these horizontal shear stresses explains why wooden beams sometimes fail by splitting longitudinally. This failure usually occurs close to the neutral axis, for reasons which will soon be obvious. So how can we calculate the shear stresses? We can calculate the average shear stress acting on the cross-section as the shear force V divided by the cross-sectional area. But the shear stresses aren't distributed uniformly across the beam cross-section. The shear stress has to be zero at the free surfaces, at the top and bottom of the beam. So the average shear stress isn't very useful, since it doesn't tell us the maximum shear stress. Instead, we can use this equation to calculate the shear stresses acting on the cross-section. I won't cover the derivation of the equation here, but it's based on considering equilibrium of stresses acting on a small element within the beam. The equation assumes that the shear stress is constant across the width b of the cross-section, so tau is a function of the distance along the beam, x, and the distance above the neutral axis, y. V is the shear force acting on the cross-section, which varies with the distance along the beam. B is the width of the cross-section. It can vary with the distance y from the neutral axis, but in this case, the cross-section is rectangular, so B is constant. I is the area moment of inertia, which is a constant value calculated based on the shape of the cross-section. And Q is the first moment of area for the portion of the cross-section above the location we want to calculate the shear stress for. So it varies with the distance y above or below the neutral axis. It is equal to the product of the area above the location of interest, and the distance between the centroid of that area and the neutral axis. If the location of interest is below the neutral axis, we consider the area below the axis instead of the area above it. To calculate the first moment of area at this line, which is at a distance y from the neutral axis, we multiply the area of the blue rectangle above the line by the distance from the neutral axis to the centroid. Doing this calculation gives us an equation for Q as a function of the distance y from the neutral axis for a rectangular cross-section. and so we can obtain an equation which describes how the shear stress varies with distance from the neutral axis. The y term is squared, and so the shear stress varies parabolically over the height of the cross-section, with the maximum shear stress occurring at the neutral axis. This is opposite to the bending stress, which is 0 at the neutral axis, and explains why the horizontal shear failure of a wooden beam we saw earlier occurs close to the neutral axis. By setting y to 0 in this equation, we obtain an equation for the maximum shear stress in rectangular cross-sections. It is equal to 1.5 times the average shear stress across the entire cross-section. The derivation of this equation for shear stress makes a few assumptions, so we need to be careful with how we apply it. First, it assumes that the shear stresses are constant across the width of the cross-section. For rectangular cross-sections, this is a reasonable assumption if the rectangle is thin. But for cross-sections like this one, the shear stresses can vary significantly over the width. And so, in these cases, the equation can really only give us the average shear stress across the width of the cross-section. It can't tell us what the maximum shear stress will be. Another assumption this equation makes is that the shear stresses are aligned with the y-axis. Shear stresses act tangentially at a free surface, so for a circular cross-section, for example, we can't strictly use this equation to get the distribution of shear stresses across the height of the cross-section. But we can still use it to estimate the shear stresses at the neutral axis, because the shear stresses there are aligned with the y-axis. The equation for shear stress at the neutral axis in a circular cross-section is similar to the equation for a rectangular section, where we have the average shear stress V over A multiplied by a constant. The constant is 4 over 3 for a circular cross-section and 3 over 2 for a rectangular one. We can also use the shear stress equation for thin-walled sections like this I-beam, although things are a bit more complicated. Because the vertical shear stresses at the surfaces shown in red must be 0, and because the flanges are very wide, the vertical shear stress in the flanges is very small. This means that the vertical shear stress is distributed like this. The web mostly carries the shear force, and the flanges mostly carry the bending moment, as we saw earlier. You can see that the shear stresses are distributed quite evenly over the height of the web. This is because the flanges contribute significantly to the first moment of area Q when calculating the shear stresses in the web, but they don't carry much of the vertical shear force. Since the web is thin, the shear stresses are also distributed evenly across its width. Because of this, we can easily calculate the approximate shear stress in the web, like this. More detailed analysis reveals that there are shear stresses in the flanges, but they are acting mainly in the horizontal direction. The horizontal stresses on both sides of the flanges cancel each other out, so the net shear force is still just a vertical force. We can figure out the direction of the horizontal shear stresses based on the direction of the vertical shear stresses by imagining that the stresses are flowing through the cross-section. That's it for this review of bending and shear stresses in beams. If you enjoyed the video and would like to see more content like this, please consider supporting the channel on Patreon. Thanks for watching.
Spray cans, rocket propellant tanks, subsea pipelines, industrial reactors, and this propane tank. They all have one thing in common. Their main purpose is to contain a fluid that's at a higher pressure than the environment. These are all pressure vessels. Pressurized fluids can exert enormous forces on the walls of the vessels that contain them. In this video, we'll explore how engineers apply simple mechanics principles to ensure pressure vessels can safely contain their contents without risk of catastrophic failure. Most pressure vessels are either spherical or cylindrical. One of these shapes handles pressure much better than the other, even though it's less commonly used. We'll get to why that is a bit later on. Let's start by looking at the cylindrical pressure vessel. It contains a fluid at high internal pressure, with the outside of the vessel seeing a lower atmospheric pressure from the surrounding environment. What we're interested in is the difference between these two pressures, the gauge pressure P. The net effect of this gauge pressure is to push outwards on the inside surface of the cylinder, causing stresses to develop in two main directions within the vessel wall. In the hoop direction, around the circumference of the cylinder, from the pressure trying to radially expand the circular cross-section, and in the longitudinal direction, from the pressure pushing against the ends of the vessel and trying to stretch it along its length. Being able to quantify these stresses is the key to safely designing pressure vessels. Let's focus on deriving an expression for the hoop stress first. We can do this by considering an arbitrary section of the vessel, of length L, and cutting it in half to examine the hoop stress within it. Remember that in mechanics, stresses develop in such a way as to maintain equilibrium. The pressure load that acts on the curved inner surface of the cylinder is balanced by the hoop stress in the cylinder walls. The resultant of the internal pressure is a force with a magnitude equal to the pressure multiplied by the projected area over which the pressure acts. This area is the cylinder diameter, d, multiplied by the length, L. The resultant of the hoop stress is a force that has a magnitude equal to the hoop stress, multiplied by the area over which it acts. This area is 2 times the wall thickness, T, multiplied by L. The two force terms must be equal to maintain equilibrium. We can then solve to obtain the famous equation for hoop stress, PD over 2T. A pressure vessel with a diameter of 400 millimeters, for example, that has a wall thickness of 10 millimeters at an internal pressure of 50 bar, which is 5 megapascals, will develop a 100 megapascal hoop stress in its walls. Reducing the pressure, reducing the vessel diameter, or increasing the wall thickness all result in a lower hoop stress. We can derive an equation for the longitudinal stress in a similar way, by taking a circumferential slice of the vessel this time. The important insight here is that the hoop stress is twice as large as the longitudinal stress. This means cylindrical pressure vessels are theoretically more likely to fail by splitting along their length rather than around their circumference, because the material reaches its yield point in the hoop direction long before it does in the longitudinal direction. The next time you're holding a garden hose, another type of pressure vessel, take a close look at the reinforcing fibers within it. Chances are they'll be oriented at exactly 54.7 degrees from the axis of the hose. This carefully selected orientation, called the magic angle, represents the theoretically optimal fiber direction for a scenario where the hoop stress is exactly twice the magnitude of the longitudinal stress. With this angle, the fibers are perfectly aligned to carry the hoop and longitudinal loads in the right proportions. With the hoop stress being the critical stress, it's the PD over 2T equation that's used to calculate the minimum wall thickness required to safely contain an internal pressure P. All we need to do is define an allowable hoop stress, which is often taken to be 80% of the material's yield strength. In welded vessels, an additional factor, the joint efficiency factor E, is often applied to account for the potentially reduced strength at longitudinal welds. It usually has a value between 0.7 and 1. A corrosion allowance is also often added to the calculated minimum thickness to account for material loss over the service life of the vessel. This is a fundamental equation used in the design of pressure vessels. The equation can also be rearranged to calculate the maximum allowable pressure for a given vessel. So what about spherical pressure vessels? The curvature of a spherical vessel is the same in every direction. This means that, at any point in the vessel wall, the in-plane stress is the same in all directions, and there's no distinction between hoop and longitudinal stress like there is in cylindrical pressure vessels. This stress is equal to PD over 4T. This is the huge advantage of spherical pressure vessels. Their shape distributes stress evenly in all directions, resulting in a maximum stress that's half the maximum stress in a cylindrical pressure vessel. In theory, a spherical vessel could be half the thickness of a cylindrical one for the same internal pressure. Despite this, cylindrical vessels are still far more common in industry. The reason is simply because they're a lot less expensive to make. Rolling plate into cylinders and welding on domed end caps is much easier than forming a sphere. Now's probably a good time to mention that we made two big simplifications when deriving the PD over 2T and PD over 4T stress equations. The first is that we treated the hoop stress as a constant value through the thickness of the vessel wall. In reality, it peaks at the inner surface and gets smaller as you move to the outer surface. The vessel wall shown here is thin relative to its diameter, so the reduction in hoop stress is small, and the assumption that hoop stress is constant through the wall thickness is reasonable. For thick walls, though, the variation in hoop stress becomes too large to ignore. The second simplification is that we accounted for stresses in the hoop and longitudinal directions, but we completely neglected any stresses acting in the radial direction. In reality, on the inner surface of the pipe wall, there will be a compressive radial stress equal in magnitude to the internal pressure to balance the normal force applied by the pressurized fluid. On the outer surface, the radial stress has a magnitude equal to the external pressure, which is pretty much zero for a vessel in air. To better understand the significance of the radial stress, take a look at the ratio of the hoop stress to the radial stress at the inner wall surface. If the vessel is thin-walled, meaning it has a large D over T ratio, it's clear the hoop stress will become much larger than the radial stress. In this case, it's acceptable to neglect radial stresses. But if the vessel is thick-walled, the radial stress becomes significant relative to the hoop stress and can't be ignored. It's common to define thin-walled pressure vessels as those with a wall thickness that's less than 5% of the diameter of the vessel. D over T is greater than 20, and a thick-walled pressure vessel for anything thicker than that. The PD over 2T and PD over 4T equations only apply to thin-walled pressure vessels. For thick-walled vessels, the hoop, longitudinal, and radial stresses are given by the slightly more complicated Lemay's equation for thick-walled cylinders. The hoop and radial stresses are functions of the position within the vessel wall. To help you keep track of all these different pressure vessel equations and when to apply them, I've created a one-page summary sheet that covers all of the important information on a single page. It's part of a growing collection of engineering summary sheets I've been developing, covering shear force and bending moment diagrams, trusses, torsion, the finite element method, buckling, and more. There are 14 sheets in total, and I'm adding more over time. Each one summarizes key equations and concepts in a quick review format, making them ideal as study aids or reference guides, great for exams, interview prep, or for when you just need to brush up on a particular topic. All 14 summary sheets are available for free for anyone who supports the Efficient Engineer channel on Patreon, and that includes any new sheets I release in the future. As a supporter, you'll also get access to video previews and behind-the-scenes details showing how the Efficient Engineer videos are made. So head over to efficientengineer.com/support to join me on Patreon. Get access to the full set of engineering summary sheets, and help me continue to create videos and develop resources for the engineering community. If you'd rather just purchase the sheets directly, you can do that too for $15. Just go to efficientengineer.com/buy. And that's it for this look at pressure vessels. As always, thanks for watching. Thanks to CuriosityStream for sponsoring this video. There are a lot of different analytical methods that engineers can use to solve structural mechanics problems, whether it's to calculate the deflection of a beam or the stresses in a flat plate. But we often encounter problems that can't be solved in this way, typically because the geometry, loads, or materials are too complex. The finite element method is a powerful numerical technique that uses computational power to calculate approximate solutions to these types of problems. It's widely used in all major engineering industries. It could be used to check satellite components will survive the launch conditions, for example. Or to optimize the design of automotive components, like the lower control arm of this car's suspension system. Finite element analysis software can be used to analyze a wide range of solid mechanics problems, including static, dynamic, buckling, and modal analyses, but it can also be used for fluid flow, heat transfer, and electromagnetic problems. For this introduction to the finite element method, we'll focus on how it applies to static linear elastic stress analysis. Imagine we want to analyze the brackets supporting this air conditioning unit. The goal of a static stress analysis would typically be to calculate the stresses, strains, and displacements within the bracket. These unknowns are called field variables. Internal stresses develop within a body in such a way as to maintain equilibrium over any volume of the body, so we can apply the concept of equilibrium to calculate the field variables. This is easy to do for a simple beam. We can use equilibrium to calculate the bending moment and shear force along it, and from there, we calculate the normal and shear stresses in the beam. But enforcing equilibrium over a two-dimensional shape like this bracket is difficult, and it becomes even more complicated for a three-dimensional body. The finite element method approaches this problem by splitting the body into a number of small elements that are connected together at nodes. This process is called discretization, and the collection of nodes and elements is called the mesh. Discretization is useful because the equilibrium requirement now only needs to be satisfied over a finite number of discrete elements, instead of continuously over the entire body. Several different element shapes can be used. We've used triangular surface elements to model this bracket. Surface elements are two-dimensional elements that are typically used to model thin surfaces. They can be triangular or quadrilateral. Triangular elements are good for modeling awkward shapes, although quadrilateral elements tend to perform better. Solid elements are used for three-dimensional bodies. And then we have line elements. Choosing the right element for your model will depend on the specific scenario being analyzed, and requires some expertise. In the case of our bracket, we could have used solid elements, or even line elements, depending on how much we wanted to simplify the problem. Even for elements of the same shape, there are hundreds of different types to choose from that each have different formulations and introduce different levels of approximation. A line element can be a bar, for example, that only carries axial loads, or a beam that can carry axial, bending, shear, and torsional loads. We can model the bracket using plane stress surface elements, because the bracket is thin and the loading is all in the same plane, but that's only one of many surface element types. These are all first-order elements, but we can also use second-order elements which have additional midside nodes and are more accurate.
For stress analysis problems, the fundamental variable we want to calculate is the displacement at each node. If we know how a body displaces when loads are applied, we'll easily be able to calculate secondary outputs like stress and strain. For each element, we can define a vector u that contains all of the possible displacements for the nodes of the element, including rotations. If we're analyzing a two-dimensional case with beam elements, each node can translate along the x and y axes, and it can rotate about the z-axis, so the vector u will look like this. Each of these displacements is called a degree of freedom. For the beam element, we have 3 degrees of freedom per node, or 6 in total, for a 3D case that increases to 6 degrees of freedom per node. A shell element node also has 3 degrees of freedom in 2 dimensions, but since the element has 4 nodes, it has 12 degrees of freedom in total. The nodes of a solid element only have 3 translational degrees of freedom. The nodes aren't allowed to rotate, and instead, rotation of the element is captured by translation of the nodes. So how can we calculate all of the displacements at every node in our mesh? For a spring, the relationship between force and displacement is defined by Hooke's law. The spring stiffness K determines how far the spring will displace for a given force. In the same way, we can think of the elements of our mesh as having a certain amount of stiffness that resists deformation. In this equation, F is a vector of the nodal forces and moments, U is the vector of the nodal displacements, and K is the stiffness matrix of the element. A 2D beam element has 6 degrees of freedom, so the displacement vector looks like this. And the force vector and the stiffness matrix will look like this. The element stiffness matrix defines how much each node in the element will displace for a set of forces and moments applied to the nodes, and so is the key to solving the displacements at every node of our mesh. It's a square matrix. The number of rows and the number of columns are equal to the number of degrees of freedom of the element. We can figure out what the terms of the stiffness matrix are by enforcing equilibrium. We'll come back to this later on in the video, but for a 2D beam, the matrix looks like this. We can think of this equation as a system of linear equations that we can solve to obtain the displacements at the nodes of our mesh. If we apply a lateral displacement to node 2, for example, and all of the other degrees of freedom are fixed, and so are equal to 0, we can use the stiffness matrix to calculate the forces and moments at both of the nodes. To make the next steps easier to visualize, let's represent the stiffness matrix in a more abstract form. This is just one element, but our overall mesh will be made up of many more elements. Let's look at a simple example where we have a mesh made up of 3 2D beam elements that we're using to model a cantilever beam. We can assemble the individual stiffness matrices for all of the elements in our mesh into a huge global stiffness matrix that defines how the entire structure will displace when loads are applied to it. Like the element stiffness matrix, the global stiffness matrix is a square matrix, and the number of rows and columns is equal to the total number of degrees of freedom in the model. The element stiffness matrices are assembled together to form the global stiffness matrix, based on how the elements are connected together. Elements 1 and 2 are connected at node 2, for example. Continuity tells us that since these two elements are connected at the same node, the displacements for both elements must be the same at the common node. So when we assemble the global stiffness matrix, the terms in the element stiffness matrices corresponding to node 2 should be summed for each degree of freedom. Element 3 is not connected to node 2, so this element's stiffness matrix should have no effect on the displacements at node 2. This is what the actual global stiffness matrix looks like for this model. It has some interesting characteristics. It is said to be sparse because it contains a lot of zeros, and banded because the non-zero terms are grouped around the diagonal. For linear elastic problems, the matrix will also be symmetric. If we modify the mesh so that the 3 elements are connected differently, the global stiffness matrix will change. In this case, we have 3 nodes instead of 4, so the matrix will be smaller, and the fact that elements 1 and 3 are connected is reflected in the matrix. An important thing to note here is that the elements are no longer aligned to the same coordinate system, so we have to transform the stiffness matrix for each element so that it aligns with a global coordinate system. We can do this by multiplying each element's stiffness matrix by a rotation matrix. Now that we've assembled the global stiffness matrix, we need to solve this equation to obtain the displacements at each of the nodes. To do this, we need to define the external loads and the boundary conditions. The boundary conditions are known displacements at specific nodes, typically because specific degrees of freedom are fixed. In this model, vertical and horizontal translations are fixed at node 1, and vertical translations are fixed at node 2, so the displacement vector looks like this. And the force vector will look like this. It includes the applied force and the reaction forces at the supports. Now we can solve the equation. We could do this by inverting the global stiffness matrix and solving the displacements from there. But in practice, inverting the matrix isn't very efficient, particularly because it's a sparse matrix. Commercial solvers mostly use methods that involve iteratively approximating the displacement vector, like the conjugate gradient method. Once we've solved the nodal displacements, we can calculate the strains and then stresses throughout the mesh. A typical finite element mesh could easily have 100,000 degrees of freedom, which would be impossible to solve by hand, and so applying the finite element method to anything more complicated than a very basic model requires the use of appropriate software. Now that we have an overall understanding of the finite element method, let's return to the element stiffness matrix to see how it's derived. The matrix shown here is for a 2D beam element, but it will look very different for different element types. Several different methods can be used to derive these stiffness matrices, and they are all fundamentally based on the concept of equilibrium. The direct method derives the stiffness matrix directly from the equilibrium equations that govern the behavior of the element. The lateral deflection of a beam is governed by this equation, for example, so we can solve the equation to obtain the stiffness matrix for a beam element. These governing equations are usually differential equations. The differential equations and associated boundary conditions are what we call the strong form of the equilibrium problem. But it's only really possible to solve the strong form for simple elements. For more general cases, we can use weak forms that describe the differential equations in integral form, instead of solving the differential equations directly. These give approximate solutions to the equilibrium equations, but are easier to solve. The first of the weak form methods is based on variational principles. One such principle commonly used for structural mechanics problems is the principle of minimum potential energy. It states that the displacement configuration that satisfies equilibrium conditions is the one that minimizes the total potential energy, where the potential energy is the sum of the strain energy and the potential energy of the external loads. By applying a mathematical technique called the calculus of variations to minimize the total potential energy, we can obtain an approximate solution to the equilibrium equations. The other weak form method is the Galerkin method of weighted residuals. In this method, the function that satisfies the differential equation is approximated as the sum of a number of assumed trial functions that each have unknown coefficients. This approximate solution is substituted into the differential equation, and an equation for the error called the residual is obtained. If we multiply each trial function by the residual and set the integral of this product to 0, we can calculate the unknown coefficients that minimize the residual. This gives us an approximate solution to the differential equation. This is a more widely applicable approach than the principle of minimum potential energy, but for stress analysis problems, both methods give the same result. Regardless of which method we use, we end up with the stiffness matrix for our element. But to apply these methods, we need to be able to describe how displacements and other field variables vary inside the element, instead of just at the nodes of the element. To overcome this issue, an element needs to have a defined function that calculates values inside the element by interpolating the values at the nodes. The shape function is just an assumption. It's usually chosen to be a polynomial, since they're relatively simple and sufficiently accurate. And with that, we've covered all of the key aspects of the finite element method. In summary, the first step in the finite element method is defining the problem, including the relevant material properties, loads, and boundary conditions. Next, the body being analyzed is split into a number of small elements connected at nodes, and the element types are chosen. Then, a stiffness matrix is defined for each element, using one of the three methods we covered earlier. The element stiffness matrices are then assembled into a global stiffness matrix based on element connectivity. This global stiffness matrix defines how the structure will respond to applied loads, and we can use it along with boundary conditions to solve for the displacement at each node in the structure. Once we have displacements, we can calculate stresses, strains, and other field variables of interest. Then all that's left to do is post-processing to obtain the desired results and validation of the model. A lot of the hard work, like calculating the element stiffness matrices, assembling the global stiffness matrix, and solving the model, is done by the software being used. But the engineer is responsible for making sure that the problem has been properly defined, that the mesh is suitable, and for interpreting and validating the results. I hope this video has helped you develop a better understanding of the fundamentals of the finite element method. If you're interested in learning more, you can check out the extended version of this video that's available now over on Nebula, where I spend a few more minutes covering the problem definition, discretization, post-processing, and validation steps. Nebula is a streaming service built by independent educational creators. It's a place where you can find extended versions of my videos, alongside amazing original content from other creators, like Mustard and Wendover, without any ads or sponsor messages. You can get access to Nebula for free when you sign up for CuriosityStream. CuriosityStream is the perfect streaming service for curious minds. It has thousands of high-quality documentaries to keep you entertained and learning, like Particle Fever, an incredible film that follows experimental and theoretical physicists during the first round of experiments at the Large Hadron Collider, the largest science experiment ever conducted, as they work to prove the existence of the Higgs boson particle. If you sign up to CuriosityStream using this link, you'll get a 26% discount on their annual plan, and you'll get access to Nebula for free, all for less than $15 a year. So to watch my bonus content on Nebula, and Particle Fever, and countless other documentaries on CuriosityStream, head over to curiositystream.com/efficientengineer, or click the link in the description. It's an amazing deal, and signing up is a great way to support this channel. And that's it for this introduction to the finite element method. Thanks for watching. We know that when we apply loads to an object, like this bracket, if we keep increasing the magnitude of the load, at some point the material will fail. But how can we predict when static failure will occur? What level do the stresses in the object need to reach for it to fail? First, we need to define what failure is. For ductile materials, failure is usually considered to occur at the onset of plastic deformation, and for brittle materials, it occurs at fracture. These points are easy to define for a uniaxial stress state, like a tensile test. They occur when the normal stress in the object reaches the yield strength of the material for ductile materials, and the ultimate strength for brittle materials. But for a more complex case of triaxial stress, predicting failure is much less straightforward. In fact, it's so difficult to predict that we don't have one universally applicable method. Instead, we have to predict failure by selecting the most suitable one of a range of different failure theories, each of which we know works relatively well under certain circumstances, based on experimentation. Because they fail in fundamentally different ways, failure theories which apply for ductile materials usually aren't applicable for brittle materials, and vice versa. So what does a failure theory do? It's quite simple. It allows us to predict failure of a material by comparing the stress state in the object we are assessing with material properties that are easy to determine, like the yield or ultimate strengths of the material that we can obtain by performing a uniaxial test. The stress state at a point can be described using the three principal stresses. So most failure theories are defined as a function of the principal stresses and the material strength. Probably the simplest failure theory is to say that failure occurs when the maximum or minimum principal stresses reach the yield or ultimate strengths of the material. This is called maximum principal stress theory, or ranking theory. Although it's simple to apply, it's not actually a great failure theory, particularly for ductile materials, for reasons I'll explain later. Let's look at some better failure theories for ductile materials. Any good failure theory needs to be consistent with experimental observations we can make about how materials fail. There is one key observation that failure theories for ductile materials need to capture, which is the fact that hydrostatic stresses do not cause yielding in ductile materials. Let me explain. A general triaxial stress state, like the one shown here, can be decomposed into stresses which cause a change in volume and stresses which cause shape distortion. Stresses that cause a change in volume are called hydrostatic stresses, because that is the type of stress acting on an object submerged in liquid. For a hydrostatic stress configuration, the three principal stresses are always equal, and there are no shear stresses. For a triaxial stress state, we can calculate the hydrostatic component as the average of the three principal stresses. The mechanism that causes yielding of ductile materials is shear deformation. Since there are no shear stresses for a state of hydrostatic stress, this component can be very large and still not contribute to yielding. Yielding is only caused by the stresses which cause shape distortion. These are called deviatoric stresses. The deviatoric component is calculated by subtracting the hydrostatic component from each of the principal stresses. The hydrostatic and deviatoric components can be expressed in matrix form, like this. Here we have described the stress state using the principal stresses, but we could also describe it for an arbitrary orientation of the stress element. It can be helpful to use Mohr's circle to understand the hydrostatic and deviatoric components of a triaxial stress state. For a hydrostatic stress configuration, there are no shear stresses, and so Mohr's circle reduces to a single point, equal to the average of the three principal stresses. Shifting Mohr's circle horizontally represents an increase in the hydrostatic component. And increasing the radius of Mohr's circle without changing the average stress represents an increase in the deviatoric component. Since failure of ductile materials only depends on the deviatoric component, a good failure theory for ductile materials should produce the same result regardless of where Mohr's circle is located on the horizontal axis. This explains why maximum principal stress theory is not a good failure theory for ductile materials. It isn't consistent with the observation that yielding is independent of hydrostatic stress. Two failure theories which are consistent with this observation are the Tresca and von Mises failure criteria. These are the two most commonly used failure theories for ductile materials. Let's start with the Tresca failure criterion, which is also called the maximum shear stress theory. It is named after the French engineer Henri Tresca, and it states that yielding occurs when the maximum shear stress is equal to the shear stress at yielding in a tensile test. This can be defined mathematically, like this, and graphically using Mohr's circle, like this. This theory is consistent with the observation that hydrostatic stresses don't affect yield. It doesn't care where Mohr's circle is located on the horizontal axis. It's common to express this theory as a function of the principal stresses, instead of as a function of the shear stresses. We can see, based on Mohr's circle, for a triaxial stress state, that the maximum shear stress is equal to the radius of the outer circle, which is the difference between the maximum and minimum principal stresses, divided by 2. Mohr's circle for a uniaxial tensile test at yielding looks like this. The intermediate and minimum principal stresses, sigma 2 and sigma 3, are equal to 0, and the maximum principal stress, sigma 1, is equal to the yield strength of the material. The shear stress at yielding is equal to half of the yield strength of the material, so we can rewrite our equation to obtain the standard formulation for the Tresca theory. Let's look at the von Mises failure criterion next, which is also called the maximum distortion energy theory. It was initially developed by the Austrian scientist Richard von Mises, but a number of others were involved in refining it, so it is sometimes called the Maxwell-Huber-Henke-von Mises theory. It states that yielding occurs when the maximum distortion energy in a material is equal to the distortion energy at yielding in a uniaxial tensile test. So what is the distortion energy? It is essentially the portion of strain energy in a stressed element corresponding to the effect of the deviatoric stresses. The distortion energy per unit volume can be calculated from the principal stresses using this equation. We know that at yielding during a tensile test, the maximum principal stress is equal to the yield strength of the material, and the two other principal stresses are equal to 0. So we can calculate the distortion energy at yielding in a tensile test by plugging in the appropriate principal stress values. And by equating the distortion energy at yielding with the general equation for a triaxial stress state and rearranging a bit, we get an equation that defines the von Mises failure criterion. Again, we can see that this theory considers the difference between principal stresses and so is independent of the hydrostatic stress. The term on the left is often called the equivalent von Mises stress. If it is larger than the yield strength of the material, yielding is predicted to have occurred. The equivalent von Mises stress is a common output from stress analysis performed using the finite element method. Contour plots are typically generated to show the distribution of the von Mises equivalent stress within a component, as these allow areas at risk of yielding to be identified. When comparing failure theories, it can be useful to plot their yield surfaces. A yield surface is the representation of a failure theory in the principal stress space, which sounds more complicated than it actually is. To keep things simple, let's start by considering a plane stress case, where one of the three principal stresses is equal to 0. By convention, principal stresses are ordered from largest to smallest, like this. But since we don't know yet how the stresses will be ordered, I'll refer to them as sigma A, sigma B, and sigma C instead. We'll say that sigma C is equal to 0, and so the two axes of our yield surface graph correspond to the two non-zero principal stresses, sigma A and sigma B. The yield surface for the maximum principal stress theory is easy to plot. It says that yielding begins when either of these principal stresses is equal to the yield strength of the material, so it looks like this. Yielding is considered to have occurred when the stress state reaches this line. Next, let's plot the yield surface for the Tresca theory. This theory states that yielding occurs when the difference between the maximum and minimum principal stresses is equal to the yield strength of the material. But it's not as simple as taking the difference between sigma A and sigma B. Plane stress is still a three-dimensional stress state. In the top right quadrant of the graph, both sigma A and sigma B are positive, and so sigma C, which is equal to 0, is the minimum principal stress. The yield surface looks like this. But in the bottom right quadrant, sigma B is negative, and so sigma B is the minimum principal stress. That gives us a yield surface that looks like this. Repeating this process for the other two quadrants completes the Tresca yield surface. Von Mises yield theory for plane stress conditions is defined using this equation when expressed in terms of the principal stresses. We can square both sides of the equation and see that it is of the same form as an ellipse, which gives us the von Mises yield surface. Let's plot some experimental data for tests performed on ductile materials and see how each of these theories compares. It's clear that the maximum principal stress theory has large areas where its use is potentially unsafe. So let's get rid of it and compare Tresca and von Mises. Both agree well with experimental observations, although von Mises agrees slightly better. The Tresca yield surface lies entirely inside the von Mises surface, meaning that Tresca is more conservative. If we assume that the principal stresses will increase in proportion to one another as a load is applied, and so the stress paths are straight lines, the difference between the Tresca and von Mises theories is largest for these three configurations. The maximum difference between the two theories can be calculated to be 15.5%. Von Mises is usually preferred to Tresca because it agrees better with experimental data, but Tresca is sometimes used because it is easier to apply and it is more conservative. So far, we have looked at a plane stress case, with sigma C equal to 0, but for a general three-dimensional stress state, sigma C will be non-zero. We know that the Tresca and von Mises yield surfaces aren't affected by hydrostatic stresses, and so to obtain the yield surfaces in 3 dimensions, we just need to extend the plane stress yield surfaces along the hydrostatic axis. Failure of brittle materials is different to failure of ductile materials. For brittle materials, failure is considered to occur by fracture rather than yielding. And unlike ductile materials, brittle materials tend to have compressive strengths that are much larger than their tensile strengths. This needs to be captured in any failure theory for brittle materials. It also means that to assess failure of brittle materials, we need to know 2 separate ultimate strengths, for tension and for compression. Coulomb-Mohr theory is a failure theory often used for brittle materials. Unlike the theories we have seen for ductile materials, it considers failure to be sensitive to hydrostatic stresses and captures the difference between tensile and compressive ultimate strengths. The easiest way to define this theory is using Mohr's circle. We start by drawing the Mohr's circles corresponding to failure in the uniaxial tensile and compressive tests. By drawing lines tangent to both circles, we create a failure envelope. Coulomb-Mohr theory states that a material will fail for a stress state with a Mohr's circle that reaches this envelope. The Tresca yield criterion we saw earlier is actually a special case of the Coulomb-Mohr failure theory, where we have the same material properties in tension and in compression. The plane stress failure surface for Coulomb-Mohr theory looks like this. As you can see, it doesn't agree particularly well with experimental data in the bottom right quadrant. Modified Mohr theory is a slight variation on the theory which better fits experimental data. It is one of the preferred general failure theories for brittle materials. Because failure theories for brittle materials need to account for the effect of hydrostatic stresses, these failure theories converge to a point when extended along the hydrostatic axis. And that's it for this introduction to failure theories. We've covered the most common theories, but there are many more out there which may be more appropriate for specific scenarios. If you enjoyed the video and would like me to cover more topics, please consider supporting the channel on Patreon. I'll put a link in the description. Thanks for watching.